Hello everyone, next up what we're going to do is proof by mathematical induction. So again, similar to contradiction, we will find out how it works. So for example, let's say I have a statement Pn, okay, that I want to prove for all positive integers. Okay, so first of all, what we do is I want to prove the base case is true. So in this case, the base case is P1 because that's the first case, this is the first positive integer. And next, let's say we can also prove that pk plus 1 is true for any positive integer k. So if I can prove that pk plus 1 is true, then if p1 is true, this means that p1 plus 1, because pk plus 1, right? p1 plus 1 or p2 is true. And again, if p2 is true, then p3 is true. If p3 is true, p4 is true. And it goes on for all positive integers. And in this way, it's kind of like a chain reaction or domino effect, where basically proving one case is true proves all the cases. So how do we actually put this into practice? Let's do a question. This question is an example of sigma notation used for mathematical induction, which is very commonly asked. My first step will be to let Pn be the proposition, and I'll just copy down what I want to prove for all n as a positive integer. By the way, please try to copy all the English words that I write to the T, because IB gives 1 mark for each of these statements. Alright? And remember, your next step is to prove P1 is true. And what we're gonna do is actually take left hand side, and if we substitute n equals to 1 into the left hand side, we get 2, 1 minus 1, which is just 1. And on the right hand side, this is just equals to 1 squared, which is 1. So this implies that left hand side equals to right hand side and P1 is true. For our next step, listen very carefully. We're going to assume pk is true for some positive integer k. And again, I want to rewrite this statement in terms of k. And for our fourth step, remember what we did? We wanted to prove that pk plus 1 is true. Usually it's not necessary to write this out, but I like to write it out because it makes it a lot easier to see what you're trying to prove. So you're trying to prove that this is actually equals to k plus 1 squared. Again, I'll take the left hand side, and what I want to do is use the pk assumption. In this case, just this over here. So how are we going to do that? I'm actually just going to split the sigma notation into k r equals to 1 of 2r minus 1. I'm going to plus the last term where r equals to k plus 1. So if I substitute k squared into here, I'll get k squared plus 2k plus 1, which we can see easily that this is just k plus 1 squared, which is just your right hand side. So this shows that pk plus 1 is true. And your final step will be to say, since p1 is true, and pk is true, implying that pk plus 1 is true, by induction, pn is true for all n as positive integers, shown. Okay, so this is an example of sigma notation being incorporated into mathematical induction questions. Okay, we'll be doing one more question just to practice induction. Prove by induction that 11 to the power of n plus 1 plus 12 to the power of 2n minus 1 is divisible by 133 for all positive integers n. So again, your first step will just to write everything down in terms of mathematical notation. And if you remember, divisible by 133 just means that this number is equals to 133a, where a is an integer. In this case, it's safe to assume that a is a positive integer, because if n is a positive integer, then this expression over here is a positive integer. Again, your next step is to prove that the base case is true. So to prove p1 is true, in this case, again, since it's all positive integers n, we take it that p1 is the base case. But for another question, maybe they could do n is more than 2, and you may have to prove that p3 is true as your base case. Okay, so don't take it for granted that you'll be proving p1 is true every single time. So to prove p1 is true, we take the left hand side, which will actually be 11 squared plus 12, and this will net us 133, or 133 times 1, which can easily let us see that this is equals to the right hand side. This means that P1 is true. Now remember, our third step is to assume pk is true for some k as a positive integer. And then I'll write down my pk assumption again. And now, our next step is to prove pk plus 1 is true. Again, I'll write down what pk plus 1 looks like. Okay, as you can see, this is just equals to 133c, where c is an integer. Sometimes the right hand side can be a lot more complex, even more complex than the sigma notation question as we saw earlier, and because of that, that's why I find it a good habit to just write down what pk plus 1 is. Again, for proving questions, you always want to keep an eye out on what you're trying to prove. So in this case, you're proving equals to 133c. The left hand side, again, 11k plus 2 blah blah blah. So what we want to do is use the pk assumption. In this case, I can't directly use this assumption, so I will just do a little bit of algebraic manipulation so that I can use 11k plus 1 and substitute that in. So let's see how that helps us. We actually just get 11 times of 11k plus 1 because of this k plus 2 up here. So if we use the pk assumption, it will look like this. And then we can just add on the rest, plus 12 to the power of 2k plus 1. What I want to do is I actually want to switch positions. I want 133 11b minus 11 times 12 to the power of 2k minus 1 plus 12 to the power of 2k plus 1. And again, it may not be so clear what I can do here, but one move that I could do is factorize out this 12 to the power of 2k minus 1. So that's what I'm going to do. I'll do plus 12 to the power of 2k minus 1. And then this left here will be 12 squared. Okay, because again, if you think about it, this is just equals to 12 squared times 12 to the power of 2k minus 1. So after our factorization, I'll get 12 squared and minus 11 over there. And would you look at that, this is actually just 133. So I can take 133 11b plus 12 2k minus 1. And we are sure that this is always a positive integer, because first of all, 11b is a positive integer. 12 to the power of 2k minus 1, since k is always a positive integer, this will be 12 to the power of some positive integer. So we are sure that this is equals to 133c, where c is a positive integer. Again, this is equals to the right hand side, which proves that pk plus 1 is true. Again, you can see that pk plus 1 is where the bulk of the math is. And for our final statement, we write that since p1 is true and that pk is true, implying that pk plus 1 is true, by induction, we can say that pn is true for all n as a positive integer. Here's the summary sheet for proof by mathematical induction. As you can see, we have done 2 questions over here, one on sigma notation and one on divisibility. Again, please remember to keep to the format and also try to keep to the proper phrasing for each statement so that you won't lose random marks. Thank you guys for watching. Hopefully this helped, and have a wonderful rest of your day. Goodbye.